All right, people, here we go with part two of this final review. And here we go. How many moles of argon are contained in a 190 milliliters vessel at 21 Celsius and 450? This, ladies and gentlemen, is an ideal gas log problem or a PIV-NERT problem. We write down PIV-NERT every time. 190 is the volume. Now the volume is in liters, so we have to put 0.19. The temperature is 21. The temperature is in Kelvin, so we have to put 294. 450 is our pressure, and that's in millimeters of mercury. So since we're using millimeters of mercury, our R has to be 62.4. That's how we do it. So we're going to solve for N. I'll ask you what is N. Now I'll show you. I'm going to cross multiply 62.4 times 294 right there. And then we'll calculate this. 450 times 0.19 divided by parentheses 62.4 times 294, close those parentheses, equals 0.00046.005 moles. All right, let's keep rolling. What is the volume? Let's PIV-NERT this. What is the volume of 1.3 moles at 1.3 is our moles at 2.5 atmospheres? 2.5 is going to be our pressure. And now, since it's atmospheres, we're going to put 0.0821 for our R at 330 K. 330 is our temperature, so we're looking for the volume. Okay, how are we going to solve for this? We're going to move the 2.5 down here. And we very simply have V is equal to this equation. 1.3 times 0.0821 times 330 equals, divided by 2.5 equals. Looks like 14.1 liters is going to be our volume. And the last one is calculate the volume of 60 grams of N2 at 211 and 792.4. Now look, this is PIV-NERT again, but what's tricky about this one is it gives us grams instead of moles. 60 grams of N2. So the first thing we have to do is say 60 divided by 28, because that's the weight there. 60 divided by 28 equals, so it means 2.1 moles. 2.1 moles. 211 is our temperature. The pressure is 792.4, and it's in millimeters of mercury, so we need to use 62.4 for our R. And we're looking for the volume. I'll ask you what that is, and you would say that divided by 792.4. Calculate that. 2.1 times 62.4 times 211 divided by 792.4. 34.9 liters. All right. Here is a graph. This is a phase change due to pressure graph. All right. This is solid. The middle's liquid. This is gas. Every time. What phase is at 40 bars and negative 75 Celsius? That's going to be right here. So that's number 48 right there. 48 is solid. I'll ask you, what phase is at 1 bar and 50? 50 degrees and 1 bar. Oh, that'd be really low. That'd be a gas. So number 49 is a gas. Now, what would a shift from number 48 to 49 be? Well, it would actually, that's a bad question. I'm sorry. Oh, this is negative 50, y'all. Negative 50. Let me go back. Negative 50. Still the same thing. Still 1 bar and negative 50. Same thing. We still have to go through 2 First it would have to melt, and then it would have to liquid to gas, then it would have to vaporize. So that's a bad question there. I'll have to fix that. When you go from solid, then you go from solid to get from there to there, it's just not a good question. I think maybe I was trying to write one where you went from solid to gas, and then that answer would be sublimate, but that's a bad question. All right, let's keep rolling. But I'm sure you understand it now that I explained it. Here are molarity problems. Molarity, this is the strength of a solution. So this is the concentration. Molarity means how salty is this water, right? So 200 grams of sodium hydroxide are dissolved in 3,000 milliliters of water. What is the molarity? Molarity means moles per liter, okay? So 200 grams of sodium hydroxide, we've got to convert that to moles. 200 grams divided by sodium hydroxide, if you add that up, it's 40. 200 grams divided by 40 grams, that's 5 moles. So 5 moles are dissolved in 3,000. So 5 moles in 3,000 milliliters is equal to how many moles per 1,000 milliliters? Now, I bet you can solve that. And what we would do is cross multiply 1,000 times 5 divided by 300 divided by 3,000. So that would be 1.67 molar. Okay, let's try the next one. 13 grams of lithium chloride is dissolved in 500 milliliters of water. What is the molarity? Okay, 13 grams of lithium chloride. Lithium chloride, the formula is LiCl. That's 7 plus 35, 42. 13 grams out of 42 grams equals 0.31 moles. So we have 0.31 moles in 500 milliliters. That will be equal to how many moles per liter, per 1,000 milliliters? We'll cross multiply. That will give us 0.62 molar. All right, number 53. 350 milliliters of water contains 5 grams of table salt. What is the molarity? We've got to convert that to moles. 5 grams divided by, and you know table salt is NaCl, so 5 divided by 58 grams. That equals 5 divided by 58 equals 0.09 moles. We have 0.09 moles in 350 milliliters of water. That's equal to how many moles per 1,000? All right. I'm going to cross multiply this. 1,000 times 0.09 divided by 350. 0.26 molar. Excellent. Now let's look at this graph here. This is the energy contained in the reactants. And then it absorbs energy before the reaction starts to take place. Then as the reaction takes place, it ends down here, and the products have less energy than the reactants. Is this exothermic or endothermic? Well, had to give off heat if it went down, right? We're down here now. Number 55, the products have more or less energy than the reactants. They have less. We're down here now. The reactants are up here. This has a positive or negative delta H. As a negative delta H, it has lost heat. Exothermic energy exothermic equations are losing heat. A catalyst would make this require less activation energy. Draw a dotted line to show the catalyzed reaction. Dot, dot, start at the same place. We begin going up, but then it's going to take less energy and it's going to finish sooner. But notice it starts and ends with the same amount of energy. That doesn't change. It just happens with less activation energy, and it gets done sooner rather than later. All right, let's keep rolling. Here's our formula for specific heat. This is Q is equal to MC delta T. I like that big triangle. That's the best I could do with Google Docs. How much energy is required to heat 45 grams of water from 140 to 143? How much energy is needed for 45 grams? So our M is 45 grams. Now it says water, but look at this. The temperature of the water is so high that it's really steam. So when we're figuring out our C, we have to look here for steam. 2.02 is the specific heat. It's the C for water. So when it's steam, so 2.02. And the change in temperature is from 140 to 143. So the change in temperature is 3. So 45 times 2.02 times 3. 272.7 joules. Okay? Now, why don't you work number 61? 2,951 joules are used to heat 212 grams of a metal from 30 to 61. So the change in temperature is 31 degrees. So what is the C? What metal was it? Okay. We're going to say 212 times 31. That's going to go on the bottom now. All right? So 2951 divided by parentheses, 212 times 31, close the parentheses, equals 0.449. And we can look up 0.449 on our chart. Page 1, we can see that that is iron. So iron, okay? 61, you lay a chunk of aluminum in the sun beside a chunk of copper, which will heat up first. The copper, which would eventually hold more heat. The aluminum. Here's our graph. Here's our questions. This is about solubility. 20 grams of ammonium chloride is dissolved in 100 grams of water at 20 degrees Celsius. Okay, see, this is grams per 100, and this is Celsius. So 20 at 20 degrees Celsius. So 20 up here at 20 over, boom. Now, if we're talking about ammonium chloride, here's the line for ammonium chloride. We're below the line, so we're going to be unsaturated. 70 grams of NH3 at 10 degrees Celsius. Here's 10 degrees Celsius. So, looks like we're maybe right on the line. Maybe right above it. I'm going to say that we're on the line. I'm going to call it saturated. Okay. And you do this last one here. This is for you. 70 grams of ammonium chloride at 80 degrees Celsius. 70 grams up here, 80 degrees Celsius. Here's the line for ammonium chloride. We're above the line. Supersaturated. equilibrium questions about this problem right here. Here we go. You should be good at this. This is fresh. Adding CO2. We add some of this, shift to the left. K doesn't change. I know that means not equal to 0, but you know that I always write that means doesn't change. We're going to increase the pressure. What's going to happen? Increasing the pressure means less gases. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 gases on this side, and there's 4 and 6, 10 gases on this side. So more pressure, less gases. But it doesn't change the K. The only thing that changes the K is temperature. Don't forget that. Write the K. K at equilibrium for this is the product CO2 to the 4th times water to the 6th. This should look super familiar with you with all the acids and bases work that we've been doing, okay? Over C2H6 to the 2nd times O2 to the 7th. And you saw how I did that. You saw how I did that. Oh, there's one more. Removing CO2 creates a shift to the, we're going to take some of this out. So we're going to go that way to replace it. There should be both arrows on this. That's a mistake. All right. We'll go that way. K still not going to change. Temperature is the only thing that changes the K. Here we go. What are you going to end up with in the end if this happens, the alpha decay of calcium 42? All right? 42 over 20 Ca would end up being, if it gives off an alpha particle, it's going to be 38 and 18. It's going to be argon 38. All right? Argon 38. All right? Write the complete equation for the beta negative decay of carbon 14. 14 over 6C, giving off a beta negative particle that's 0 over negative 1B. That's an electron, isn't it? And what minus 1 is 6? 7. What and 0 is 14? 14. That's nitrogen, regular old nitrogen 14. Beta positive decay of lanthanum, what's that going to give us? 137 over 57 La. Beta positive, that's a positron, okay? It's a positron because it has no weight. 137 over 56. And that's barium. Barium 137. All right. Let's keep rolling, people. Just about done. Talking about half-lives now. The half-life of 131. Oh, I'm sorry, it's supposed to be iodine. The half-life of iodine 131 is 8.07 days. If 15 grams are left after 40.35 days, how many grams are in the original sample? Okay, 40.35 is the time, and 8.07 is the half-life. So that's going to be 5. 5 half-lives went by, okay? So that means if we have 15, then we had 30, and then before that we had 60, then before that we had 120, then before that we had 240, and before that we had 480. So we can just work that one backwards. 480 were in the original sample. You can also say the final amount is equal to the original amount times 0.5 to the half-life over, to the time over half-life. You could also do that. I'm going to ask you for the answer to this one. Okay? You can use this formula if you want to. Write it down. Okay? The half-life is 3.8 days. 3.8 days, all right? The time that went by was 15.2 days. How much is left? 120 grams was our sample. So we're just using the formula for this one, just doing it this time with the formula. Right? This formula is this original times 0.5. So let's just do this with the calculator. That's no problem. 120 times 0.5, y to the x, parentheses, 15.2 divided by 3.8, close the parentheses, equals. Looks like 7.5. 7.5 grams would be left. All right, what's the pH? 0.01. Very simply, that's right, the pH is equal to 2. The pOH will be equal to 12, wouldn't it? What's the pH here? Well, the pH is the negative log of the molarity. So we type this in, 2.234 EE, 6 negative. I just typed that in. And then now I'm just simply going to hit log negative. pH is 5.65. Okay, excellent. Last one, this is one where you actually have to do all the math. 0.325 grams of hydrochloric acid and 1.5 liters of water. We need to figure out how many moles that is. So we'd say 0.325 divided by 36. That's 0.009 moles in 1.5 liters of water is equal to how many moles per 1 liter of water? So this is a concentration problem first. Divided by 1.5. That's going to give us 0.006. 0.006 molar. And now if we want to find the pH, we know the molarity is 0.006 molar, and we just hit what? 2 buttons on our calculator. That's right, log negative. pH is equal to 2.22. Nice. We're getting there, people. We're finishing. All right. We're going to assign A, B, C, D, E, F, or G to these problems right here, okay? All right, so I'm going to ask you, which one of these letters did you think would be hydrochloric acid from our lab? Probably going to be G, straight up hydrochloric acid. Orange juice. That's reasonable. All right. All of the OH producers, which letter up here do you think stands for? This is an arrow going this way. This is an arrow going this way. I don't know if you can read that as well at home. Okay? So which letter do you think will be all of the OHs? That's right, D. That's all of the OHs. All of the H producers. That's right, E. Ammonia, man, that's going to be the strongest base that we dealt with. Correct, F. Water. If you missed that one, I'm pretty much angry with you. And then bitter chocolate. Bitter chocolate. That's going to be a base. So I'm going to choose the weakest base that we have here and say that maybe that would be C. And I'm not really sure. I don't think bitter chocolate would be that bitter, but that's the only reasonable choice we have. I feel like bitter chocolate would really be more like this right here. But I feel like you know what I'm talking about because we just did this. All right, here we are at the end. Last thing, titrating. M1V1 equals M2V2. We just did these problems. I'm going to work this one. I'm going to ask you the next two. What is the molarity of an acid in which 30 milliliters can be neutralized with only 10 milliliters of 0.5 molar? So this is M1V1 equals M2V2, right? Solve for M1. So we have 0.5 times 10. 0.5 times 10 divided by 30 equals So the molarity is equal to 0.17 molar, okay? Now, I'm going to ask you to solve 85. M1V1 equals M2V2, go. And there's the answer, M1V1 equals M2V2. I had to put the 40 down here, got